Okay, so today I thought we would start looking a little bit at rocketry, because the natural motion of projectiles as ballistic problems where they're only subject to external forces is fine and dandy, but sometimes it's nice to be able to have thrust. So what we're going to do here is we're going to basically derive the rocket equation, the Tsiolkovsky equation, which is, at least in empty space, a nice relation with how the speed of an object depends on its mass as it's ejecting material out of its back. So here's the basic idea. We'll play a lot more with this in more exotic settings later on, but for now, let's do a one-dimensional rocket. So I'm not really worried about an arcing projectile. We're just in deep space or something like that. We'll derive something kind of general, and then we'll look at a couple examples. So first off, the whole idea behind the rocket equation, or the Tsiolkovsky equation, is conservation of momentum. We really are saying that we've got some rocket which has all of its fuel, or has some cargo fuel, all kinds of stuff inside of it. Total mass is m at some time. It's moving along with some velocity, we'll call it v. And then a later time, a little bit of mass falls out of it, or maybe it's blown out of it. And so this little bit here represents the exhaust. Now, my rocket will now have a new mass. It's the original mass plus whatever the change was. Now, be very careful here. One place that I know I got mixed up when I first learned about this in college was keeping track of the sign of dm. dm is a negative number here. The rocket's mass as a complete system is decreasing. Some of it just fell out the back. But it's convenient to write it as plus dm, so that we really are writing down some sort of differential equation for m, the mass of the rocket. So I'm going to write the rocket immediately after something comes out the back as m plus dm. It's now moving at some new speed, v plus some little change in v. This bit will be positive, hopefully. And then there's a second object, which is that little chunk of exhaust, that little infinitesimal bit of exhaust. Its mass, a positive number, is negative dm, because dm is itself negative. Don't forget that. And it'll be moving with some velocity. Now we have to figure out what that velocity is. And maybe just as a reminder, I'm looking at this whole thing from some sort of external perspective, like an inertial frame watching this rocket move by. I'm not in the rocket making these measurements. So for me, I would probably compute this as the velocity of the exhaust, maybe I'll call it the exhaust as E, relative to my inertial frame. That's what I want to write down here. How did I get this number? What does this even mean? Well, it's the velocity of the exhaust with respect to the rocket plus the velocity of the rocket with respect to my inertial frame. This is the Galilean transformation of velocities rule. And this slash notation it's not standard, but I like it. It means A with respect to B. So this is what I actually want to write, the velocity of the exhaust with respect to me in my external godlike inertial frame. And then I'm just sort of introducing the rocket frame as a third frame. And honestly, this velocity is the one that is somewhat controllable by the people on the rocket. I'm going to call this velocity U exhaust. So EX stands for exhaust. Please note, that is the velocity of the exhaust relative to the rocket. It doesn't care about how fast the rocket is traveling. It just cares about how fast it's being ejected from the rocket. This is totally a function of things like the nozzle aperture area, the pressure differential, the combustion rate, etc. All of that stuff about how the rocket is actually mechanically ejecting the material is all hidden inside of this exhaust velocity. This piece, however, is the velocity of the rocket with respect to me, but that's just v. Now, there's a bit of quibbling you can do over whether this is this v or v plus dv. Maybe I'll even include a little dv just in case. I don't know. Is this the velocity of the rocket right at this moment, or was it the initial? It turns out it won't matter, because that extra little differential change in velocity is totally negligible compared to the velocities themselves. We'll see how that works in a second. Okay, so all of that is pretty important. But then, of course, what are we going to do with all this? We're going to apply conservation of momentum. Or actually, we're going to do something a little more general. Maybe the momentum of this system is not conserved, and I'm going to instead invoke the impulse momentum theorem aka Newton's second law, just rewritten. Let's not forget that the net force on any system, and here my system is the rocket and all of its exhaust. Everything is my system. So this will be external forces only. If you want to include some sort of internal force between these, the rocket pushes that way and the exhaust pushes back, you know by the third law that those two are equal and opposite, so they would cancel out if you did include them in this sum. But Newton's second law says that the net force on some system is the rate of change of that system's momentum, dp dt. This is slightly different than the MA version, but that's just because my mass is changing. I can't use the MA version. This is actually the version that Newton wrote down, and that's the one that's going to apply here, at least non-relativistically. All right, so now what we're ready to do is try to compute dp, the difference. It's a tiny difference, but the difference between my final momentum of the system and my initial momentum of the system. So I'm going to write that as dp is going to be p final minus p initial. The final momentum of this system, everything's non-relativistic, is just the mass times velocity of all the pieces. That's the rocket piece. I also have to include the momentum of the mass. And notice that its velocity is kind of long. I'll even go ahead and include the extra little dv, just in case you're worried about that distinction between immediately before, immediately after. And then I'm going to subtract my initial momentum. But of course, that's just mv. And I'm dropping all the dependence on t here. Almost everything here depends on t, or even could depend on t. Okay, let's see what happens when we expand this out. So first off, we're going to see something nice happening with the mv's here. So I'm going to have an mv from here. I'll have a plus m dv plus dm times v plus dm dv. This piece will give me a minus dm times v. I'll have a minus dm times the exhaust velocity. Got to go on to the next line here. Minus dm dv, and then minus mv. Okay, so that just comes from expanding. We notice that this mv and this mv cancel. This dmv and this minus dmv cancel. Now, we do actually have a cancellation of these two terms, but even if we didn't, so let's pretend for some reason that you don't like my argument that this should include a dv, which is fine. I don't believe it myself. But even if that was the case, what's left over is mass times a first order differential, another velocity times a first order differential, and if this didn't cancel, I'd have a product of two first order differentials. In other words, a second order product. But you know that eventually, when we take some kind of limit here as dt goes to 0, I'm going to end up only keeping these first order terms. Any second order terms will be negligible relative to the first order terms. And this happens a lot in physics. In fact, I'm sure a lot of math professors or whatever might disagree with the idea of thinking about this dp dt as a quotient of infinitesimals. They tend to really argue against the idea of separating them like it's actually a ratio. And to be fair, I get it. I think that the mathematics community had such a collective trauma in the mid-1800s when they realized after centuries of use that calculus was not on the firmest, rigorous analytical footwork that it needed to be, that the entire development of analysis and the real definitions of calculus in terms of limits really started around that time. And people were so unnerved by the idea that we've been using calculus this whole time. It could be wrong, or it could be non-rigorous, non-analytically proven, that everyone from that time, Weierstrass, etc., all collectively really pushed their students to not think of these as infinitesimals, and they pushed their students to not think of infinitesimals. And even to this day, our calculus teachers are still paying forward that 150-year-old jump scare. Physicists never had a problem with this. Newton himself, who invented calculus for physics, did not think in terms of limits. He wrote these little infinitesimals. Everything was sort of fluxions, I think is what he called them. And yes, you can make the theory of infinitesimals more rigorous, but it's totally fine for you to think of these as little tiny chunks. The main reason is in physics, in the real world, all of our functions are continuous. They're continuously differentiable. We're not going to have weird, bizarre, pathological functions where limits need to be properly taken. Everything can just be thought of as nice little well-defined differentials. So if you're a physicist, don't worry about it. Treat them like a ratio, treat them like little multiplicative infinitesimals, that's fine. If you do want to do this rigorously, what you would do is write these all as deltas with a delta t, then you'll divide by the delta t at the end, we're about to here, and take the limit as delta t goes to 0, and you will see that my delta will go to literally the number 0 in the limit. Okay, so now what we're ready to do is smush all this stuff down together and write my net force. So my net force on the system is just this dp divided by dt. So I'll write that as m dv dt. That's my first non-zero term here. And we recognize an old friend, dv dt, that's the acceleration, ma. That sounds good. We've got something we're kind of expecting. But there's a new term, something very interesting over here. What is this? What's this? So this is something new. It's related to the rate at which the mass of the rocket is changing. And notice dm dt will be a negative number. Can't stress that enough because the mass of the rocket is decreasing as it ejects stuff out. By the way, this still would be true if I had like stuff sticking onto the front of the rocket and adding to its mass, so you could still write it down that way. But for us, we're really thinking about this as a negative number. And so we're going to do something that looks a little weird here, maybe at first. I like to think of this as ma, my usual sort of right-hand side of Newton's second law. So I'm going to move this term over. And I'm going to think of this as a new force, as a new type of force that I'm adding to all the other forces that might be gravity, drag, etc. Now we should note that, well, it is a force in a way, but what it's really doing is, when you move this over to solve for m dv dt, you're only talking about the rocket now. You're talking about this part. You're not examining the exhaust anymore. And so it makes sense that the dynamics of the rocket, not including its exhaust, should be whatever external forces there are, plus the force that the exhaust exerts on the rocket, the action-reaction pair as these two things separate. We know they push on each other with equal and opposite forces. You might ask, what is that force? Here it is. We call this force thrust. So from here on, when I'm analyzing a rocketry problem, I will just treat the rocket as having a variable mass. Don't forget that m is now a function of time. Its acceleration is some kinematical quantity I'm usually interested in. There may be external forces, and then I will also add a thrust force. We should be a little bit careful about the signs. I already mentioned dm dt is a negative number here. This u exhaust vector, well, it's a vector quantity, and you might notice that over here, I kind of treated everything as moving to the right. And really, of course, the exhaust velocity in a normal rocketry problem, unless stuff is sticking to the rocket, is going to be opposite the direction of motion. So be careful about the direction of this exhaust velocity. What direction is the exhaust being spat out? That will usually also be in the negative direction, at least opposite the acceleration. And so you'll end up with kind of a negative, making this an actual forward-pointing force that will tend to accelerate the rocket. Okay, so this is where we're going to start for now looking at a special case, which is the rocket in free space. And we're going to solve this differential equation to get our Tsiolkovsky equation. Okay, so here is our equation in the absence of any external forces. Later, we'll probably look at the influence of gravity, but let's start off simple. And let's just imagine this is moving in the x direction to make life a little bit easier. Okay, nice and easy. I went ahead and said that my velocity for the exhaust is in the negative x direction. So we pick up a negative sign from the vector nature here. And let's also make the assumption, which is a very common assumption here, that dm dt is a constant. I'll call that constant b. This is the mass ejection rate, right? It's mass per unit time. We kind of have two different factors that go into our thrust equation. What is the speed at which the mass is ejected, and also how much mass is being ejected per unit time. And you can imagine both of those could be controlled independently, or at least they might be related, but they could be independent. If I take a giant boulder and I just push it out the back of my rocket, well, I probably didn't push it very fast, but I might have moved a lot of mass when I did that. So both of them can matter. I do know that dm dt is a negative number. We've already said that many times. So I'm going to put a negative sign here, and then this b will be a constant. If you want to deal with a variable mass ejection rate, go for it. But for now, I just want to think about the mass as being ejected at a constant rate. Notice that that immediately tells me what m of t is. I can integrate this equation, and it's going to be m naught minus bt. So my mass, the m that's going to show up on this side, is actually this equation, if we needed it. Let's say that m naught is the starting mass. That's the rocket plus all of its fuel, and then it gradually gets depleted. That means that there's going to be some burnout time. Sometimes that's convenient to define for various kinematical reasons. So after this time, you've got no more fuel, so no more thrust. So this will last only until this particular time if we burn it at a constant rate. Okay, so this is actually already in a very nice separable form. Let's go ahead and just multiply both sides by dt, which is totally fine if you're a physicist. And then I'm going to separate the m to the other side. M does depend on t, but we don't really need to figure out what this is as a function of time. The Tsiolkovsky equation is usually written as a function of mass, which we can then, using this, turn into a function of time if we want. Integrating both sides and assuming that our exhaust speed stays constant, we're starting at some initial mass m and going to some arbitrary final mass. We could have started with a non-zero initial speed, I guess. That's fine. Maybe our rocket was sort of coasting for a bit, but if you want to set that to 0, you can. And of course, the 1 over m gives us a natural log. Let's go ahead and do one last bit. I'll move the v naught over. I'm actually going to flip this fraction in here at the cost of making this a plus sign. The reason for that is m is less than or equal to m naught. You're decreasing in mass. And the log of a number less than 1 is negative. So instead of having to play with this double negative game, let's keep everything positive. Okay, this is at least one version of the Tsiolkovsky equation. It tells us that my final speed, or my speed as a function of how much mass I have of my rocket, is whatever initial speed, ignore that if we need to, the exhaust speed, which might be quite high, times a natural log of my initial mass divided by the mass at the instant of interest. This natural log is very, very frustrating to rocket scientists. The reason why it is hard to launch rockets, the reason why it's hard to put things into orbit, to get to the moon, etc., is that dang natural log. Because natural log is a very slowly growing function. So yes, I can make m naught bigger and bigger, but if I say double or even take up my mass that I start with of fuel by a factor of 10, I only gain logarithmic advantage. I don't gain any scaling factor. And the reason for that is because, well, yes, you've increased the amount of mass, but you've got to carry all that fuel with you as you're burning it. So the mass that you have to accelerate also grows. And so we don't get this nice double this, you get double out. It doesn't work that way. We don't even get a power law. We just get a log. Okay, if desired, though, and you want to know this is a function of time, then v of t would just be this natural log that has this, this time dependence built in that we found earlier. All right, so this is our v of t. Maybe the next thing we'll do in a future video is can I use that to find my position as a function of time? Of course you can. You just integrate this. We'll make this into a dx dt or something, and this integral is not too hard to do if you know how to do the integral of log. And then we might want to also start thinking about a either two-dimensional version or starting to include other external forces like gravity or drag. Ex principio sequitur.